Today, I have to discuss the working principle, that is the physics of transistor, and the name transistor arises from the action of transfer of resistor in this new semiconductor device after the discovery and establishment of PN junction semiconductor diodes. It is invented in 1947 at Bell Laboratory jointly by Professor John Bardeen, Professor Walter Brattain, and Professor William Shockley. It is a bipolar semiconductor device based on the motion of both electrons and holes, and it has three terminals named as emitter, base, and collector. And the significant properties of this transistor is that it transfers its resistance from one PN junction to another PN junction, and hence it amplifies AC signal and power. Now let us first consider the fabrication mechanism of NPN transistor. For this, we consider pentavalent atom arsenic doped N-type substrate as a starting material for transistor body. Then an oxide layer of silicon dioxide have been deposited on this N-type substrate. Now a portion of this N-type substrate is thermally diffused by trivalent boron atom through SiO2 window to form a lightly doped p region. Again, a portion of this p region further diffused by pentavalent arsenic atom to form a heavily doped N plus region. After that, metallic contacts are made to the N plus and P region through the oxide windows and to the N region at the bottom. In this way, we form three terminals named as emitter, base, and collector. So, by this mechanism, we achieve two ideal PN junctions spaced distance apart in a single bar semiconductor material or substrate. Also note that the physical size of the collector region is largest with its doping intermediate of emitter and base region. Now, the action of a transistor basically depends on the properties of a PN junction diode, which operates under forward and reverse bias only, and the role of depletion zone is the only significant parameter in that case, where we know that when P and N type semiconductor are brought together, electron and holes migrate across the junction and a depletion layer is formed. As a result, a potential difference is set up across the depletion layer. Again, note the same significant properties. Therefore, on the basis of the formation of depletion zone at the PN junction, we note that for an NPN transistor under zero bias condition and at thermal equilibrium, we get two depletion layers, one at the emitter base junction and another at the collector base junction. Here, A stands for the pentavalent arsenic dopant atom and B stands for trivalent boron atom, and the dot indicates the free electrons and the circle indicates the free holes in the semiconducting material. Note that the depletion regions are free from any mobile charge carriers like electrons and holes, and the ionized arsenic and boron atom are mutually interacted by the static electric field developed in between them, and the electric field and the contact potential difference in the depletion region reacts like a potential barrier for further diffusion on depth of charge carriers through this depletion zone. As a result, we get no current through any of these depletion regions under zero bias condition, and at dynamic equilibrium we know that the drift and diffusion current under dynamic condition is of the such order that the net current will also be zero. Also, note that as the doping of the base region is least, the extension of the depletion layer in the P side is larger. So the effective width of the base region is less than the actual width of the base region, and it should be of the order of diffusion length of the carriers in the base region to minimize the electron hole recombination in the base region. Now, when the emitter-base junction is forward biased by the voltage VBE, the depletion layer potential barrier height and the space charge layer almost vanishes, leading to sufficient emitter current by diffusion of charge carrier across the junction. On the other hand, the reverse bias applied by the voltage VCB across the collector-base junction increases the potential barrier height and the immobile space charge layer, leading to approximately zero current, neglecting the reverse saturation current across this junction. Therefore, it may be considered as a transfer of resistor from emitter-base junction to the collector-base junction, and from which the device is named as transfer of resistor and abbreviated as transistor. Now, the mechanism of transport of charge carriers through a biased NPN transistor may be explained from its energy level diagram under emitter base at forward bias and collector base at the reverse bias, where EC is the lower energy level of the conduction band and EV is the upper energy level of the valence band, and EF is the corresponding position of the Fermi level for N and P type semiconducting material, and these are the free electrons moving in the conduction band, and these are the holes moving in the valence band. Now we observe that the forward bias emitter base narrow depletion zone with very negligible space charge, and this is the collector base reverse bias depletion zone with wider depletion zone and huge number of immobile charges. Now at the forward bias junction, due to reduction of the depletion layer width and the potential barrier height, most of the free electrons diffuses from emitter to the base region or the P region, and if the effective width of the P region, that is the undepleted portion of the P region, is smaller compared to the diffusion length of the electron, then high concentration density at the edge of collector base junction results further diffusion of this electron into this reverse bias field collector base junction, where they swept out or float up by the existence of high electric field, and the drift motion of this electron results huge current at the collector. Also note that some holes from the P region also diffuses to the emitter side, resulting some emitter current, and very few electrons and holes recombine at the P region, that is the base region, resulting some base current. Also, we note that very few holes, that is the minority charge carrier at the N side, and some electrons in the P side may drift through this collector base reverse junction field, resulting in some collector current, and this is known as reverse saturation current. But this reverse saturation current, that is actually undesirable for very good performance of a transistor, because this reverse saturation current results some heating effect at the collector junction, and due to this heat, to minimize the heat, we always consider the wide width of this collector region and the good heat dissipation heat sink at the collector side. And this reverse saturation current also creates some noise when we use transistor as an amplifier. The flow of different charge carriers through the NPN transistor may also be summarized from this schematic diagram, where these are the injected electrons from the emitter side into the base region. And in the base region, the high accumulation of this electron easily diffuses into the collector base reverse bias junction, where these electrons easily drift by the existing electric field of this depletion zone of the collector base junction, and they are collected by the collector terminal, creating the collector current. And very few of the injected electrons recombine with the lightly doped p-region holes, and this recombination constitutes the hole current. And few holes of the p-region also diffuses into the emitter side, and these injected electrons and holes constitute the total emitter current. And these are the minority holes in the n side, and this is the electron in the p side, minority electrons. And these minority charge carriers, that is a hole and electron, very easily drift through this collector base reverse bias depletion region electric field, and the flow of this electron and hole minority carrier flow constitute the reverse saturation current. Finally, the different current components in NPN transistor due to the flow of electrons and holes through the forward bias emitter base junction and reverse bias collector base junction have been depicted here, where INE is the current, emitter current due to the flow of electrons from the emitter side to the base region, and INC is the electron current at the collector terminal due to the flow of electrons from the p side to the n side. And the difference of these two components is the recombination current, which is INE minus INC, and IP is the hole current to the emitter region due to the flow of holes from the p side to the n side. And the sum of these two components, that is INE and IP, constitute the total emitter current. Now, IACBO is the hole current due to flow of minority holes from the n side to the p side through the collector base depletion region, and INCBO is the electron current due to the flow of minority electrons from the p side to the n side, and the sum of these two currents constitute the total reverse saturation current ICBO when the emitter terminal is open. And the sum of these two current, that is ICBO with its INC, constitute the total collector current. And from Kirchhoff's law, we may write that IB equal to IP, that is this component, plus INE minus INC with its negative part of ICBO, because the ICBO is in opposite direction to this component, that is IP, and this recombination current. Now adding this base current IB with its collector current, we get IE equal to INE plus IPE, because this ICBO nullify with this component of negative ICBO. Similarly, INC also nullify by this minus INC component. Therefore, finally we get the total emitter current equal to the sum of collector current and base current, and this equation is valid for any type of transistor circuit which operates in the active region. Now, at the conclusion, the essential principle of transistor along with the frequently asked questions from the students may be explained from this diagram, where this is the emitter base junction and this is the collector base junction, and this is the immobile spaced layer of the depletion region of the collector base junction, and this is the electric field profile we have drawn here. And at the junction we observe the maximum electric field, and at the edge of the depletion region the electric field vanishes or reduces to zero value, and outside the depletion zone we observe that there is no existence of electric field. Now the questions arises from the student that In spite of the existence of negative ions in the base region of the depletion zone, how this free electron of the base region diffuses into this region? The answer is that these negative ions will not repel these free electrons because these negative ions are only mutually interacted by the electrostatic force of the positive ions of this depletion region. Therefore, this free electron will feel free to diffuse into this region, and where they will float up or drifted by the electric field of this region to produce a large current. Therefore, in transistor, we note that a controlled injection of carriers into the reverse bias junction from a nearby forward bias junction. Hence, we can modulate the current flow in one junction by changing the bias on the another. And the goal of transistor is to use a small input to control a large output.